Hey, cool. Last part of our discussion electricity is what we actually use electricity for, and that's building machines. So we need to know how machines work and how to read circuits. So what you're going to do today is you're going to learn about the basic parts of circuits, and then tomorrow we'll learn about how to basically take a circuit diagram apart. And the goal will be for every item in the circuit, every element in the circuit, we want to know its resistance, its current, its voltage drop, and the power it dissipates. So we want to know the resistance of the device, the current through the device, the voltage dropped across the device, and the power dissipated by the device. All those prepositions are just kind of proper. So current runs through, voltage is, or potential is drops across, and power is dissipated by. Yeah. So we're going to use V equals IR and P equals IV a lot. Tomorrow we're going to learn something called a VERP chart to make all of our calculations pretty easy. One thing we need to discuss, and this is a big one, and it rubs some people the wrong way, current is a positive charge. So current runs from a high potential to a low potential. And in this basic diagram, which is composed of one voltage source and one resistor, the long pole is the high potential. So this is the high potential over here, and this is the low potential over here. The long pole is the high potential, the short pole is the low potential. Maybe it's plus 90 and 0. Maybe it's plus 12 and 0. Maybe it's plus 1.5 and 0. So, without blurting it out, is the current in this basic resistor traveling clockwise or counterclockwise? If you believe, so give yourself 5 seconds to decide, is it traveling clockwise or counterclockwise in this diagram? This is the positive side, this is the negative side. This is the high potential, this is the low potential. So, if you believe it's traveling clockwise, raise your hand. If you believe it's traveling counterclockwise, raise your hand. And you'd be right. Yep. So it's traveling from the high potential to the low potential. Now, current, once again, guys, this is one of those things that you can be like, okay, Mr. Byers, I get it. But then you on a test, you'd be like, I thought it was the electrons. Current's positive. Electrons are flowing in the opposite direction. So by convention, it is the positive charges that are moving. Current is, by convention, positive. The electrons are moving in the opposite direction. So the current's moving counterclockwise through the circuit. Am I making that more complicated than it needs to be? Or are we good? Okay, current is positive. Good. All right, so current may flow through series sections when there's only one path, or a parallel section where there's multiple paths. Just like your traffic on the freeway may travel in one path or in multiple paths. And in our house, our current, or our circuits, are basically two types of circuits. DC, which is direct current, and AC, which is alternating current. On your devices, DC looks kind of like this. It's like that, representing a positive and a negative. AC looks like half of a sine wave. AC is alternating current, where the current shifts back and forth. DC, there's a constant flow of positives that way and negatives that way. With AC, it's constantly flipping. Positive, negative, positive, negative, positive, negative, positive, negative. 60 times a second. Why? Yeah. Turns out that if we want electricity to go really long distances, we need to crank up the voltage to keep from losing a lot of electricity, losing a lot of power, creating a lot of heat. So if we crank up the voltages really, really high and allow the voltages to swap, then we won't lose power due to heat. If those power lines that are running from the dam to Los Angeles were pulling 110,000 DC power, they get extremely hot and would eventually melt. But 110,000 volts AC, they don't do that. We can transfer the power to Los Angeles very, very efficiently through mechanisms that I do not know. I don't know the actual mechanism for it, other than you can basically think of it as turning on and off. Hey, So I apologize. You can probably figure out why AC is better at long distances. I'm just here to tell you that AC is better traveling over long distances. Any questions, or any other questions before we move on? That was an excellent question. I wish I had the answer to it. Yeah.
Wasn't Tesla the one who went AC?
Mm-hmm. Yep, and we'll talk about him. Okay, so everything on this slide you've already seen. Okay, so you don't need to write down. We're just going to review it quickly. So we're going to continue to use the analogy of electrons traveling, or current in this case, traveling through wires, works like water traveling through pipes. So just like water flows downhill, and we would need a pump to pump it back uphill, voltage sources create artificial potential differences. They take a source that is high on one side, low on the other side, and the current wants to move from the high to the low side. So just like we would pump water uphill and allow it to flow downhill, we're going to pump current to a high potential and allow it to flow to a low potential. And remember that anything that uses current creates resistance. And much like air traveling through a wind turbine slows the air down, and water traveling through a water turbine slows the water down, when current travels through a resistance, it slows the current down. So we extract energy out of the wind by slowing the wind down, we extract energy out of the water by slowing the water down, and we extract energy out of the current by slowing the current down. Does that idea make sense? Okay. And remember that a circuit must be closed for current to travel, and we're going to learn how to diagram circuits with important symbols that I'm about to show you. Okay, AC/DC, who's this guy? DJ? Tesla. Who's this guy? Edison, yeah. So there was this battle between Tesla, who thought AC would be better, we should build our entire infrastructure on AC. This is the end of the 19th century. 1880, 1890, when electricity is basically going from, hey, that community has electricity, to, hey, we should make the whole United States have electricity, which was not 50 states at the time. And then, so basically, Edison did his play, and Tesla did his play. One of them was far more charismatic than the other. And I'm going to let you research it. You probably already did when you were doing the crossword. Yeah, Edison was a really good businessman. But Nikola Tesla had some really, really good points. He said, like we were talking about before, if you want to send electricity from a dam to downtown, 80 miles away, you're going to lose a lot of energy if you send it through DC. AC is handy. And Edison said, well, that's great and all, but once electricity gets here, it has to be DC. We have to use DC so we can power our iPads and our plasma screens. Well, they were both right. Okay. So we use both. In our devices, in our iPads and our plasma screens, we have to use DC. And our batteries, our electrochemical cells, also function on DC. It's a direct current. Yes?
Wait, so what would be wrong with AC in short distances?
Nothing's wrong with AC at all in short distances. It's just devices can't use it. You can't use AC in your calculator. You can't use AC in your iPad. Computers, transistors upon which computers are built, do not run on AC. They run on DC. So nothing is wrong with AC. We could wire the entire universe in AC, which is what we did, but then we need those little boxes to convert the AC in the wall to the DC that digital balance can use. So nothing's wrong with AC. Something is wrong with DC. Again, we can't send DC over long distances without the wire heating up and producing lots and lots of heat and losing power from that heat.
That's what that plug is, like when you have an iPhone and the. Wow.
Yep, that's exactly what that is. Yay, learning. Yeah.
Is that why when you leave your phone in for too long, heat does it just keeps pumping current into it?
If that happens, you have a really bad power supply. So that should not happen. Once your battery is charged up to the point where your battery is effectively full, then the power supply should turn itself off. If it doesn't, you just have a crappy power supply. Yeah, they should get warm because they have to do a lot of math. They have to basically do a lot of conversions. The conversion from AC to DC is kind of interesting, and I'm going to totally slaughter it for you in a little bit. So DC is what we get out of batteries. Your cell phone battery works on DC. All batteries work on DC. Some generators work on DC. AC is really good, like I said, over long distances. We call it alternating current. And I have no idea why, you could probably look this up and tell me, I have no idea why we chose 60 hertz. In other words, that positive, negative, positive, negative, positive, negative. I don't know why they chose to have it alternate 60 times a second instead of something higher like 100, or what Europe uses, 50. I don't know why they chose 60. Apparently, maybe Tesla was 60 years old when he finalized it. I don't know. Yeah, I don't know why they use 60, but we use 60 times a second. So it alternates positive, negative, 60 times a second. And I know what you're thinking. Mr. Byers, if the current is going this way, then this way, 60 times a second, does that mean the current doesn't go anywhere? Well, effectively, no. Because the current's traveling every 60th of a second, it's going that way, creating an electric field pretty close to the speed of light. And then every 60th of a second, it's going that way, pretty close to the speed of light. So a lot of current's moving. It's just not all moving at once. Going moving extremely fast. 1/60th of a second is a long time when you're creating electric fields that are acting near the speed of light. So anyway, the next question, again, like Jared asked, what's that big block doing? I will show you what it's doing. And again, transistors and diodes are good at doing math. You can do math too. What it's doing is it's taking the sine wave that comes out of AC, where this is a positive zone and this is a negative zone, and it's taking the absolute value of the sine wave. So you take the absolute value of the sine wave, and now you have two humps. And then they take an average of those two humps. And this part fills in that part, and this part fills in that part. And you basically get a rough DC current. That's roughly what's going on.
So that's how it transforms into DC from AC.
Yeah. You take the absolute value, and then you basically average it out by constantly charging and discharging capacitors, and then using a transformer to step up instead. And we'll talk about transformers when we talk about magnetism. But you're basically taking the sine wave, flipping the negative into positive, and then using that to charge up things and discharge and charge up and discharge and charge and discharge. So you can kind of level stuff out and take the humps and kind of squish them flat. But anyway, so yeah, your cell phone works on DC, and the AC is basically converting that DC into AC. The cool thing is, if you had a perfect system, the AC power going in would be DC power coming out. If you had a perfect system, we know that your resistors get a little hot, the blocks get a little hot, so you're not a perfect system, but it's close. Okay, I'm going to blast through circuit diagrams. I'm not going to show you all of the circuit diagrams that exist in the world because, well, if you really want to learn about circuits and like to the point where you're capable at building them, that's just a 1 or 2 year course in college. Electrical engineering is a big deal. So we're going to learn the very, very basic, probably the 5 most basic things. Okay, first one, a battery or a cell is given a long line and a short line. The long line represents the high potential, and the short line represents the low potential. Yes? There's no reason. It used to be, it's actually a really good question. It used to be that an electrochemical cell was given 2 lines, one for the high potential and one for the low potential. And then a battery is multiple cells. So this would be a cell. And then if you had multiple cells, you'd show how many you had by showing multiple lines. But nowadays, there is no convention. It's just, it doesn't really matter. Do 2, do 6, do 4, it doesn't matter. It's always going to be an even number, though. And fun fact, since you mentioned it, the batteries that you guys are going to be using to build actual circuits with these super cool things, these take AA batteries. AA batteries are not batteries. Sorry. Yeah, AA batteries are not batteries. They're cells. This is a 1.5 volt electrochemical cell. 1.5 volts. It uses a chemical reaction where the electrons want to move from the high potential to the low potential, and they have 1.5 volts of potential to move. There's 1.5 volts of wanting them to move from the high potential to the low potential. This is a cell. This is a cell. This is a battery. A 9-volt battery is actually a battery. A 9-volt battery is 6 ones of these. 6 of these squished into a little rectangle, and you get a 9-volt battery. This is a battery. Because then you wouldn't get a lot of current. They wouldn't last very long. Somewhere along the line, somebody said, let's make all commercial batteries, or electrochemical cells, this big. And, well, here we are. We have smaller batteries now, those little disc batteries. But yeah, so most of our Thomas the Tank engines run on these. Our little Thomas the Tank engine toys, AA batteries.
Why are they considered cells?
Because there's one chemical reaction going on in one chamber. So there's one chamber and one chemical reaction going on in here. In here, there's 6 separate chambers with 6 separate chemical reactions. Your car battery is also a battery. It's a battery of 6 2-volt chambers. 6 cells, each of 2 volts. Ish. 2, 2.2.
So how many chambers do you need to have to meet the minimum requirements of the battery? Or just always 6?
No, it just happens to be 6 by coincidence. There are batteries that are 6-volt batteries that have 4 of these, 4 electrochemical cells. Yeah. So there you go. So that's why. The long answer is that's why. There is no convention now. Just the long pole is the high potential. The short pole is the small potential or the low potential. I'm going to show resistors the American way, but you need to know there's another way to show a resistor, which is a lot better way, much like the metric system. There's a lot better way to show resistors, and people in other countries use it, but not us, because we're Yankees and we think we're the best. So if I want to show that this resistor is 10 ohms, I need to write somewhere near it, it's 10 ohms. But in Europe and Asia, all they do is they give you a box, and they write 10 in the box. But since the College Board still uses squiggly lines, we're going to keep using squiggly lines for resistors. But just understand, if you happen to be repairing your Nintendo DS and it says, it basically gives you a schematic on how to do it, it's probably going to give you the circuit with a resistor in a box with a number in it. That's how most other countries show resistors. Okay, lamps and motors are shown with squiggly lines with circles around them. Okay, because a lamp and a motor, they're resistors. They are devices that use resistance, only they're converting their heat. A light is converting its heat into light, and a motor is converting electrical energy into motion. But anything that has resistance is a device, and it's a squiggly line with a circle around it. I usually just go line, squiggle, circle. That's how I draw a device. So that's a resistor. That's a device. I just find it easier to draw them that way. We talked about capacitors a long while back. The proper way to show a capacitor is 2 parallel lines or a parallel line and a C, representing the 2 plates where the charge is separated. Parallel lines, plates with the folded up, zapping people. And hopefully you understand what a switch is. Switch has to be closed for a circuit to work. Gesundheit. No, you have to explain it to me. And then a ground is shown like an arrow of downward potential. So the ground is shown like an arrow of downward potential because a ground is just, well, a ground. So most of the time, our circuits are going to be loops, but if you don't have a loop, you can just ground things. In fact, in this class, everything is going to be a loop. Everything is going to be a loop. We won't use any crazy grounds. But it is kind of fun. If you look at the circuit diagram of most things in your car, they don't have loops because, well, why? Does anyone know why that is? Why, if you look at circuit diagrams for things on your car, why it's not a loop? Fair enough. But fun fact, you learned this in auto, I hope you would. Your entire car's chassis and everything metal attached to it is one gigantic wire. It's one gigantic negative pole. So your engine is grounded to your battery, and then the chassis is grounded to the engine and everything else. So if you want to connect a light bulb to your car, you only need one wire to go to your battery, and then one little wire to go to anything metal in your car. Your whole car is one gigantic ground. It's really neat. Makes installing stuff in your car really, really easy. Because you only need effectively only one wire. Like in my car, I have one 18-foot 4-gauge wire going from my battery to my trunk, which then connects to a power distribution block, which then connects to my amplifier and my digital signal processor for my stereo. Big, long 18-gauge, or 18-foot 18-gauge, or 18-foot 4-gauge wire. But then to ground my distribution block, it's a little ground wire about this long. Because it goes right to the bottom of the seat. Because the whole seat is wired then to the battery. Kind of neat. Okay, any questions before we move on? Moving on. All right. Series circuit. Series basically means one after another after another. So in a series circuit, there is one path for current to flow. Really old, crappy Christmas lights used to be in series. There was only one path for current to flow. And if one bulb burned out, they all burned out.
You just said that.
Right. If you have old Christmas lights that do that, throw them away.
But they're so much better just because they have the socket.
So in this circuit, by the way, does the circuit move counterclockwise or clockwise? Does current move counterclockwise or clockwise in the circuit? Counterclockwise, moving like this. Okay. Now, the circuit is moving counterclockwise from the positive pole to the negative pole, from the high potential to the low potential. But is it moving through the resistor, then the light, then the light, then the resistor, then to the switch, then back to the battery? No. The whole wire is chocked full of electrons. It's kind of like if Xylee had at one end of a pipe and Camille had the other end of the pipe. And it was full of marbles. Every time Xylee put a marble into the pipe, what happened to the other end of the pipe? Yeah, so every time Xylee added a marble, Camille will get a marble. Make sense? That's how electrons work, that's how current works. The current doesn't pile up. So it's in here already, we just need to cause it to move. And the battery causes it all to move simultaneously. So the current doesn't travel through this one, then this one, then this one, this one. It's all traveling simultaneously. And it's all traveling at the same speed, which we'll talk about in a little bit. A parallel circuit is one where you have multiple paths. And the paths don't know what other paths are doing. So here we have two paths. First path has a light and a resistor. Second path has a light and a resistor. If this light burns out, this light stays on. If this light burns out, this light stays on. The vast majority of things that you encounter in life are wired in parallel. Your house is wired in parallel. Street lights are wired in parallel. It would be very strange if one street light went out and causing them to all go out. It would also be very strange that you couldn't use your hair dryer unless your electric razor was going. So, yes, for guys.
What's this?
Yeah, some of us use electric razor 5 years ago. But anyway, yeah, so it'd be like, yeah, my house is special. We wired my kitchen in series. So in order to make toast, I have to be running my blender.
It's quite noisy in the morning.
It's very noisy in the morning, exactly. Yeah. In order to use my television, I have to be running my lawnmower. You know.
What? What is that?
So your house is wired in parallel, whereas each of these outlets around the room are all wired in parallel to a central source. They're independent of each other. But there is something in the house that is wired in series, and it's very, very important. What is wired in series in your house? In other words, wired with other things together, joining them all together. Your breakers, exactly. Your breakers are wired in series. So if you happen to be running your toaster and your waffle maker and your griddle and your blender, those are all independent of each other, but they're all tapped into the breaker because the breaker says this wiring is only good for 30 amps. If you exceed 30 amps, I'm turning you all off. Another thing that's wired in series is your GFCI, your ground fault interrupter. And ground fault interrupters are pretty cool. They basically are designed to save you if you decide to kill yourself by putting a toaster in your bathtub. They monitor the current in a circuit, and if the current suddenly drops, the GFCI kicks in and turns off the circuit. So the GFCI is there to keep it not only from spiking, but also dropping. So if you're like, it drops because all of a sudden you put the bathtub or the toaster in the bathtub, the GFCI turns off. This is the little switch with a red light and a black, or a red button and a black button in the middle. That's the GFCI. In America, probably almost everywhere, I would imagine, if you're going to install electrical outlets within 2 meters of any water source, it has to be in a GFCI. If you have a house built before 1950, that might not be the case. So you should probably upgrade your wiring. Yeah, good luck. Good luck in southern Nevada. Okay, some other devices. A voltmeter is what we use to measure potential difference drop on a device. And voltmeters are always used in parallel. By contrast, ammeters are always used in series. So back to our water analogy, if you wanted to measure how much water was traveling or how high a water was traveling over a waterfall, you'd look at the top of the waterfall, look at the bottom of the waterfall, and subtract the heights. If you want to know how much water was traveling in the river, you have to wade into the river and put something into the river. So similarly, if you want to know how much current is traveling through a wire, you have to put your ammeter into the circuit. But if you want to know how much voltage is dissipated or drops across the device, then you connect the leads in parallel at either end of the device. This is one of those things that even if I say in the next 2 minutes, does everyone understand this idea? And you all say, we understand. Some of you, when you're building your circuits on the computer or building your circuits in real life, will be like, Mr. Byers, he got 3.5 volts and I got 0.003 volts. Something's wrong. I'm like, yeah, because he put his ammeter in series and you're trying to put your ammeter in parallel. Or he put his voltmeter in parallel and you're trying to put your voltmeter in series. So you've got to make sure they're set up properly. It's probably not going to tell you, your voltmeter is probably not going to tell you that you're doing it wrong. You just need to know it. So voltmeter, little probes on either side. Ammeter into the circuit. And a fuse, kind of alluded to it a few times, a fuse is a device that clicks off if the current is too high. It may be a permanent fuse, where there's a little piece of metal that melts, and when it melts, it breaks the circuit. Or it may be a switchable fuse called a breaker, where a little spring engages and throws a switch over. Unless your house is at least 30 or, I'll say 40 years old, unless your house is more than 40 years old, you probably have a breaker box. A box of little black switches that can be switched back. Old houses and cars still use fuses. I don't know why cars don't use breakers. They all use replaceable fuses. I think it's just so AutoZone can sell fuses. But if you short circuit your radio and your radio fuse blows, you have to take out the little fuse out of go under your steering wheel, take out the fuse, put a new one in. The fuse will melt. If you want to see your fuse box, just look under your steering wheel. Yeah. A breaker is a reusable fuse. With a fuse, there's a little piece of metal, and when there's too much current, it gets too hot and it just melts, breaking the circuit. But a breaker is basically a spring and a pin, and if it gets too high, it moves away from the pin and breaks the circuit, and you can basically switch it back to put it back to where it's supposed to go. Is that your question, too? I'll go with your question.
If your house doesn't have a breaker, that's much.
Mm-hmm. Yep. And I've only seen 1 or 2 houses in my lifetime that had what are called bus fuses, and they're basically, they screw in like a light bulb. And I only do that because when I was a kid, I went to somebody's house, and he thought it would be really funny to pull the fuses out of his friend's house. my Nintendo turned off. Okay. Oh yeah, and they used to put the fuse boxes outside.
That's not smart.
Yeah.
That's very smart.
And that's not, when I say used to, there are still houses that still put the fuse box outside. Yeah. I don't know why you'd want to do that, because if you wanted to rape somebody, first thing you want to do is cut their power. Right? That's what you see in movies, they always cut the power and electricity.
How about you extreme? That's a little bit of a graphic example, but
What?
I just want to put the toaster inside.
I know if I wanted to like beat somebody up or murder someone in their house, I'd cut their power first.
Yeah.
I'm cool
Have
with
you ever
the
seen
beating up
Hush?
or murder.
No.
This is a bit of a
It's the
difference.
movie, and it's like a girl that's deaf, and like the guy, she lives in the middle of the woods, and the guy like cuts her power, so she can't like.
Okay.
Yeah.
Thanks for sharing. Kirchhoff's rules. This is one of those things. Kirchhoff's rules are one of those things that you just kind of learn while you're doing it. This is the first year I'm actually giving its own slide. The reason is because I used to just teach the way it worked, and then there was an AP question that said, basically to the effect of, what is the significance of Kirchhoff's second rule? And they're like it's easy. But anyway, so Kirchhoff has 2 rules. First rule, voltage exiting the battery must equal the voltage drops in each element. So the voltage drop exiting the battery must equal the voltage drops in each element. In other words, the sum of the voltage all the way across must be 0. The water that starts in the ocean ends back in the ocean. Or to be less esoteric, if this is a 12-volt battery, then what's the voltage drop in V1? If these are all identical, say these are all identical resistors, 12 volts is the battery, then V1 has to be what? 4 volts. And V2 has to be 4 volts. And V3 has to be 4 volts. It's kind of like if you went up a ladder, here. You climb up a ladder to the top of a slide. You're going to go down the slide. The slide looks like this.
That looks very painful.
So you climb up 12 feet, then you drop 4 feet, then you drop another 4 feet, and you drop another 4 feet.
Down both of
Does that make sense? So you can think of the circuit this way. The voltage source is pumping the charges up to 12 volts. They lose 4 volts in V1, 4 volts in V2, 4 volts in V3. Kind of like if you climbed up the ladder, you climbed up 12 feet, you go down 4, then go down 4, then go down 4. Yep, here, hold on. Here, and here, all here. Don't forget, for the bonus. Now, if there was a 4th,
What are they? Yeah.
I'll tell you later. If there was a 4th resistor and it was identical, then what's the voltage drop here? 3 volts here, 3 volts here, 3 volts, and 3 volts. Okay. So 3 plus 3 plus 3 plus 3 is 12, just like 4 plus 4 plus 4 is 12. That's Kirchhoff's first rule. Kirchhoff's second rule basically says whatever current you got going in, you got coming out. Okay. Whatever current goes in has to come out. You don't lose current anywhere. These are all expressions of one very important rule. Exactly. Energy is conserved. The conservation of energy. These are all expressions of the conservation of energy. So Kirchhoff's rule number 1, whatever voltage you got going in has to be what you got coming out. And rule number 2, whatever current you got going in at any point has to be the current going out. Okay. Questions? Then off we go. Moving right along. Okay, series circuit. Once again, a series circuit has one path. Much like a single lane freeway, due to construction or an accident, you can only go as fast as the slowest car. Similarly, in a single path, all the current is traveling at the same speed. It's traveling at the lowest possible speed, and it's all traveling at the same speed. So, if you were to slow down and slow down and slow down the devices, the equivalent resistance would be the sum of all the slowdowns. Let me draw that. Throw out a number. What's the voltage in the battery?
49.
49. Why not? So 49 volts. Okay. So if there's 49 volts in the battery, and the first resistor dissipates how much, if the first resistor drops how much voltage, what's the voltage drop in the first resistor? 10. What's the voltage drop in the second resistor? 10. What's the voltage drop in the third resistor? How about 29? Okay, it has to be equal to 49. Okay, so that's Kirchhoff's rule number 1. Make sense?
Yeah.
Okay. Now resistors. Let's look at resistance. We're going to work backwards. What's the resistance of the first resistor? 56 ohms. What's the resistance of the second resistor? 42 ohms. What's the resistance of the third resistor? 7 ohms. What's the resistance of the battery? 105? Sounds good. 105 ohms. Okay? So in a parallel section, each resistor slows down the current of the whole path. So it slows it down, and it slows it down, and it slows it down. What this does not mean is the current's going really fast and slows down, then slows down more, then slows down more. You have to add up all the resistances, and that's the resistance everywhere. Does that make sense? Okay. The current can't pile up. So the battery sees this resistor, and this resistor, and this resistor as though it only saw one 105 ohm resistor. So because current can't pile up. It can't go fast and slow, then slow, then slower. It can't pile up. So the current's traveling everywhere at the same speed. Give me a thumbs up if that idea makes sense. Moving right along. Okay, the total voltage, again, Kirchhoff's rule number 1. And what can you say about the current? So the total voltage drop is the sum of individual elements. What can you say about the current in a series circuit? No, but it's like if you had one lane of travel on the freeway, one lane of travel, what are the cars doing? They're all moving at the same speed. So current is the same everywhere in a series circuit. Everywhere in that path, current is the same. Given to us by Beagle's or So take another 15, 20 seconds, and then we're actually going to look at a series circuit. And when we are evaluating circuits, we always do the same thing. We look at the resistance of an element, the current of an element, the potential of an element, and eventually tomorrow we'll add the power of that element as well. Remember, power is energy divided by time. any questions before we move on and look at an actual, very simple circuit?
Can we not change it yet?
Okay, be quick. Quick. There's only 6 minutes left in class.
All I do is sit here and suddenly my existence is the problem.
Yeah, I know. Welcome to my life. Okay. So consider this circuit here. Okay. So we have a 45 volt voltage source, a 5 ohm resistor and a 10 ohm resistor, with our ammeters and our voltmeters placed in the proper places. V1 tells us the voltage of R1, V2, R2, and so on. So first question: what is the equivalent resistance? In other words, what is the resistance that the battery sees? Oh, really? Yeah, 15 ohms. 5 plus 10 is 15. So the battery doesn't know it's connected to a 5 and a 10. As far as the battery is concerned, it's connected to 15 ohms of something. Make sense? Next, what's the current in the circuit? Try again. V equals IR? 3. So the current is 3 amps. 3 amps in the battery because 45 divided by 15 is 3 amps. If it's 3 amps in the battery, what does Kirchhoff's rules tell us it's right there? 3 amps. And what is it right here? 3 amps. And right here? 3 amps. And right here? And right here? And over here? Yeah, because current is the same everywhere in a series section. Okay, current is the same everywhere. Well, now that we have the current through this resistor and the current through this resistor, what is the voltage drop of resistors V1 and V2? In other words, what is V1 and V2 reading? Yeah, V1's reading what? No. Yep. V1 is reading 15 volts. What's V2 reading? 30 volts. And to ask ourselves, are we satisfying Kirchhoff's first rule? Is a total voltage drop the sum of the drop of individual elements? It is. So the total voltage drop is 45 volts, 15 through the 5 ohm resistor, and 30 through the 10 ohm resistor. Make sense? Okay, you're getting there? All right, you can always watch the view on YouTube. Okay, in just a second we're going to talk about parallel circuits. Are there any quick questions about series circuits? Okay, we're going to do Burke charts tomorrow. Parallel circuits. Parallel circuits have multiple paths. And the thing about parallel circuits is just like traffic. If you had a 1-lane freeway that suddenly branched into 3 lanes because they emptied out the accident, what happens to the traffic? It speeds up. So when you have more paths, even though paths themselves have resistance, by adding more paths, you actually reduce the resistance in the circuit. People have a problem with this. Because even though they know it, on tests, what I usually hear is, oh, I knew that, or I know that one, or I can't believe I got that wrong. Because just like optics, look what parallel resistance has. Reciprocals. Yeah. Remember the focal point in the DI-DO thing? Remember that? Well, it's back. So we've got reciprocals again. So the total resistance of a parallel circuit will always be lower than the individual branches, which seems weird. You can add resistors to a circuit in parallel, but by adding branches, you actually reduce the overall resistance. That's just the way parallel branches work. The more branches you got, the faster your current is going to travel. Okay. I wish I could go further than this, but I'm not comfortable going any further because the bell's going to ring in a minute. So I'll just give you your practice worksheet, and then we'll pick it up tomorrow.